Okay, today we're going to look at section 7.6, probability and permutations and combinations. So we're going to be relating probability to what we've learned about permutations and combinations. Earlier discussion of theoretical probabilities, the first step we took was to write out the sample space for the experiment in question. For many experiments, that method just isn't practical. For example, you might want to find the probability of drawing a particular 5-card poker hand. Since there are 52 cards in a deck and the order of the cards doesn't matter, the sample space for this experiment has 52 choose 5, or 2,598,960 possible 5-card hands. Even if we had the patience and space to write them all, sorting through the results to find the outcomes that fall in our event would be just as tedious. Luckily, the formula for theoretical probabilities doesn't require us to know every outcome in the sample space. We just need to know how many outcomes there are. In this section, we'll apply techniques we learned earlier in the chapter, such as the multiplication rule for counting and our permutations and combinations to compute probabilities. So using permutations, recall that we use permutations to count how many ways there are to put a number of items from a list in order. In this case, order matters. If we're looking at an experiment whose sample space looks like an ordered list, then the permutations can help us find the right probabilities. So a bag of letters contains C, 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 D, D, I, T, 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 Y, 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 Y. What is the probability that 4 letters chosen at random will spell in order city? So, in order, permutations, which makes sense since we're talking about permutations. So the first thing we need to do is find out how many 4-letter combinations of these letters. To do that, we need to know how many letters we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we know that n equals 16, and we are choosing 4. So how many permutations do we have? Well, 16p4, which by our formula is 16 factorial over 16 minus 4 factorial, which gives us 16 factorial over 12 factorial, which gives us 16 times 15 times 14 times 13 times 12 factorial over 12 factorial. 12 factorials cancel out, and we end up with 43,680 possible 4-letter combinations. Now we have to look at how many ways we can get city in order. So looking at the C, I have 4 C's and I only want one of them. Well, we're looking at 4p1, which is 4 factorial over 4 minus 1 factorial, 4 factorial over 3 factorial, 4 times 3 factorial over 3 factorial, or 4. Now you'll see this. When we were choosing 1 from 4 in this case, there's 4 possibilities. So anytime you're choosing 1 from any number of items, it's going to be that number of items possibilities. So in the case of an I, we have 3 I's. Writing down our 4 here. So 3 possibilities for I, and 3 possibilities for T, and 4 possibilities for Y. And that is our Using our multiplication rule for counting, we multiply those and we get 144. So there are 144 ways to spell city using these letters in order. There are 43,600 total four-letter combinations, so our probability, and we'll just call it the probability of the event, E, is 144 over 43,680. And that is it. Okay, so now let's look at combinations to compute probabilities. If the sample space of our experiment is one in which the order doesn't matter, then we would use combinations. Order doesn't matter, combinations, to find the number of outcomes in that sample space. So at a charity event with 58 people, 3 raffle winners are chosen. All receive the same prize, so order doesn't matter. You are attending with 4 of your friends. What is the probability that at least one of you or your friends will win a raffle prize? And then it gives a hint. Find the probability that none of you wins and use the formula for the complements. So if you remember, the probability of E is equal 1 minus the probability of the complement of E. We want to know what is the probability that one of my group of 5, myself and 4 friends, wins. So it suggests finding the probability that none win. So that means to find out the total number of possible groups of winners, we have 58 C3, which is 58 factorial over 58 minus 3 factorial, 3 factorial, gives me 58 factorial over 55 factorial, 3 factorial, which gives me 58 times 57 times 56 times 55 factorial over 55 factorial times 3 times 2 times 1. 55's cancel out, and I get 23,426. Oh, wait, that's backwards. One moment. 30,856. So that's the number of possible three people groups out of the 58. Now there's 5 of us, so that means there's 53 people that are not in my group. That means our modified n is 53. We want to know how many ways 53 people, or correction, my modified r, no, my modified n, that's correct, is 53. I want to know how many 3 people groups I can get out of 53 people that are not my friends or me. Because this would be how many groups none of my group are winners in. So again, we have 53 factorial over 53 minus 3 factorial, 3 factorial. 53 factorial over 50 factorial, 3 factorial. 53 times 52 times 51 times 50 factorial over 50 factorial times 3 times 2 times 1. The 50 factorials cancel out, and this is the 23,426. 426. So now, there are a total of 30,856 possible groups of 3. There are 23,426 possible groups of 3 that do not have me or my friends in them. So the probability of none of us winning, which would be E complement, is equal to 23426 over 30856, which works out to be roughly 0.76. So going here, I have 1 minus 0.76, which is 0.24. Okay, if you draw a hand of 5 cards from a standard deck, what is the probability that 2 cards are spades and 3 cards are hearts? Well, going back to the beginning here, there's how many possible hands. So we don't need to necessarily do that again. Now what we need to do is find out how many ways we can get 2 spades. Well, so let's do this. Make a note here, spades. We have 13 spades and we're taking 2. So n equals 13 and r equals 2. So we're looking at, and order doesn't matter here, 13, 2. So 13 factorial over 13 minus 2 factorial. And remember, the order doesn't matter, so we're talking combinations, so don't forget to divide by the 2 factorial. So I have 13 factorial over 11 factorial 2 factorial, which is 13 times 12 times 11 factorial over 11 factorial times 2 times 1, which comes to 78. Then 3 cards are hearts, so looking at the hearts again, we have 13 hearts, but we're going to pick 3 of them. And again, it is combination, so we have 13 choosing 3. 13 factorial over 13 minus 3 factorial, 3 factorial. 13 factorial over 10 factorial, 3 factorial. Which gives me 13 times 12 times 11 times 10 factorial over 10 factorial times 3 times 2 times 1. 10 factorials cancel out. And that leaves me with 286. So using my multiplication counting rule to figure out the total number of possible hands I have that have 2 cards that are spades and 3 cards that are hearts, 78 times 286. And I get 22,308. So now the probability of the event I'm looking for is simply 22,308 divided by 2,598,960, which gives me roughly 0.0086 or 0.86% roughly. Okay, and that finishes our section 7-6.